left over. Before the break, we did, so that was before the break, we did confidence between, right? Two situations where sigma is known. Continued confidence intervals. We're now looking at proportion. And so again, simple random. Population at least 20 times as large as the sample. We have two categories. Generally speaking, a success and a failure. And there must be at least 10 individuals in each category. So NP is at least 10, and NQ is at least 10. And so we still have our standard critical values from last time, or from the time before. And so that was from when the standard deviation was known. And obviously this would be a z-test and not a t-test. You should already have those values written down. Now remember, p hat will be x over n, and as the sample size, x is the number that fall into the success category. Right, then you have your margin of error. Which is your z critical value times the square root of p hat times q hat all over n. Right, and then the confidence interval's the same. It'll be p hat minus e to p hat plus e. So right now, there's really only one difference between this and the mean, and that's how I calculate margin of error. And then we have sample size. Here are two conditions. If you already know p hat, and if you don't. We generally call that second one the worst case scenario. Yeah, remember I used the ceiling function, which does just round up. So same thing. This is known as so you may see that. I'll ask you to find the population size, assuming worst case scenario. Streaming service. Survey 600 subscribers, finds that 132 say that they primarily watch on a mobile device. We want a 90% confidence interval for the population portion of all subscribers who primarily watch on mobile. And deal with the later. Right, so p hat, x over n. X is 132, right? It's the number in the sample who prefer to stream on mobile, divided by the total number surveyed, 600. Question is that reduce down nicely. It does. That is exactly 0.22. So I will actually use the decimal in this case. We know the sample size was 600. We should probably check the conditions. So 22% of 600, we're satisfied there. 10% 60, we need at least 10, so we're good. Well, that means that there's greater than 10 remaining. So we have more than 10 in each category. Conditions are satisfied. Margin of error. We're first going to need our z-score, our z-critical value. So this is a 90% interval, right? What's this one? 1.645. That's one of those 4 known. Margin of error would be that critical score. 1.645 times the square root p hat times q hat. P is 0.22, Q is what, 0.78. And that whole thing divided by 600. We can go to one decimal place more than given. The confidence interval, again, always just your statistic minus margin of error to statistic plus margin of error. So that's going to be what? One nine two to 0.248. Remember, what is that interpretation? We are 90% confident that the true proportion is in that interval. Marketing blog claims that 30% of subscribers primarily watch on a mobile device. Is that consistent with our interval? What would 30% be as a decimal? Zero, right? That's not in there, is it? Not consistent. Our sample doesn't support this claim. So I guess that's just what I'm right. Factory is going to inspect 400 units and finds 68 are defective. We want a 99% confidence interval for the true proportion of defective units. And then we'll tackle P later. And P hat, a sample proportion. $68 over 400, right? Which is nice. That is exactly 0.17. And it's 400. Our critical value. %, is one of the 4 values that they gave. $2.576. Margin of error. 2.576 times the square root. 0.17 times 0.83, 1 minus 0.17, all over 400. Point 0.04 8 4, let's say. This one is correct. And the last one I forgot about that z-score being 3 decimal places. So I'll route the 4. Right, one more than we have. We start p hat minus our margin of error. And then we go up to p hat plus margin of error. That would be the 99% confidence interval. Okay? Could the true defect weight or defect rate plausibly be 25%? So is it plausible based on this interval that 25% of units are defective? All right, it's not in there. Of course, notice the wording between the two. But I'm not saying that the claim is false. And the first one, I just simply said, our sample doesn't support it. Second one, I'm saying it's not plausible based on this sample. Because we can't say for certain, can we? If we could, we don't need the interval. In a survey, 150 smartphone owners, 93 say they regularly use mobile banking. 95% confidence interval, the true proportion of smartphone owners who use mobile banking. This we're going to do on a calculator. Remember, we're going menu statistics, confidence intervals, right? Here we want a one proportion Z test, one proportion Z interval. Right? We don't want the Z interval because that's for means. The good news is it's not asking me if I want to do it from data or statistics. We want the number of successes. Give us 93, right? And the sample size. And then the confidence level, which for us was 95%, right? So I can just leave it. And then just as before, it'll give us values. There's our p-hat, margin of error, re-give sample size. There's the lower and upper limits of the confidence interval. And so it would go from 0.5423 to 0.6977. And as with the others, right, just be sure that you can get to this on your calculator before the exam. Also, probably before we look on the test. Campus survey of 80 students, 29 report having a part-time job. Construct a 90% confidence interval. Well, that sample size is pretty small. This one, let's actually verify the conditions are satisfied first. So, what is 29? Well, actually, yeah. So 29 greater than 10, right? That condition satisfied. If 29 report have a part-time job, is more than 10 going to be in the opposite category? That would be right. $80 minus 29 is definitely more than 10. Good. Conditions are satisfied. Actually, take that text. Go to the same place. Once again, you want the one proportion z interval. X 29 out of 80. This time it was 90%, right? Put it as a decimal. 0.90. All right, so our lower limit for the interval, 0.2741. And the upper limit, 0.4509. Again, the interpretation being, we are 90% confident that the true proportion of students with a part-time job is between 0.2741 and 0.4509. Quality team inspects 220 shipments, finds 150 meet a new on-time delivery standard. 95% confidence interval. Conditions are definitely satisfied here. Well, that's a bummer. Unfortunately, there isn't a function in Excel that would give us the margin of error. And Excel doesn't give confidence intervals. Yes. I doubt it. I don't think it's under data analysis. No, bummer. So we're gonna have to do this the old-fashioned way. Here's what I'm gonna do, I think. Start with the sample size, which is what, 220? Start with, or then we'll do the number of successes, 150, was it? There a P hat? No, of course not. I'll just write it out that way then. B2 divided by B1, right? So that's that. We already know Z. This was a 95% confidence interval, right? For 90%, what's the value of, or 95%, what's the value of Z? What is it? For 95%, what is the Z score? We go 1 point, actually, it's here because it's Excel, 1.960, right? Alternatively, you could use the inverse standard norm feature on Excel, but that's already known. We already know this value, so I'm not worried about it. Margin of error. E4, right, it's Z times square root of P hat times 1 minus P hat, that's Q hat, divided by n. There's the margin of error. Call the confidence interval lower, the confidence interval upper for the lower bound and upper bound. Remember, lower bound, p hat minus e, right? So b3 minus b5. And the upper bound, p hat plus e. And there'd be your bounds for the confidence interval. So sadly, Excel doesn't give us that nice feature to do it automatically like the calculator does. Company wants to estimate proportion of customers who prefer a new logo. They want a 95% confidence interval, margin of error at most 0.03. We're going to look at two conditions. P hat is given, and a worst case scenario where we don't know anything about it. In either case, it's going to be the ceiling give me the ceiling of that. P hat Q hat times E over Z all squared, or just E squared over Z squared. Where we know E, we take it to be the largest it can be is 0.03. We also know Z, the Z value, right? 95% confidence interval, what's Z? And I'll use the CR because that's what they give. For part A, they give us that a pilot study found about 0.45. So we're going to use that. over and plug this into Excel. Right, or your calculator, you can use either one. Excel has the ceiling function. My calculator also has the ceiling function. It's a bit more of a pain about finding on my calculator though, which is why I'm just going to stick with Excel. So let's just come over here. All right, remember it's ceiling.math, and we just need the number now. Now we just typed in the formula. It was what? It was p hat times q hat. You don't feel like calculating q hat, it's 1 minus p hat. Times e squared divided by z squared. That's not right. What happened? Oh, that makes that up. I did. Okay. That's an easy enough fix at least. Back in. Actually mixed up the formula. It's supposed to be z over e. So z squared over e squared, not e squared over z squared. So that's what it should look like. That's what it should look like. And then when I go back to the slide, I'll fix that. That should give you the right answer. $1,057. Now for B. First, let's fix that. Worst case scenario. So what we want to do is, since we don't know anything about the proportion originally, we want to maximize our sample size. Well, it can be shown that to maximize the sample size, since the z and the e are constant, the only value that's going to change is the p hat and q hat. And it can be shown using calculus that that maximum is going to be 0.25, which is when both p hat and q hat are 0.5. which is why it's 0.25 there in the formula. Because we're taking a 50% proportion. That maximizes sample size. That's why we call it the worst case scenario. You can just use the 0.25. You don't need to say that he has 0.5. I'm just doing this to explain why we're using it. So this time, ceiling.math, it'll be 0.25 times z squared divided by e squared. (1068) as a worst case scenario. You want a minimum sample size of 1068. Again, remember what this calculation is giving us, actually giving us the minimum sample size required. A larger sample size reduces the margin of error, which is obviously better. That's it on confidence intervals. In summary, for confidence intervals, the process is the same. It's always your statistic minus margin of error to statistic plus margin of error. What's changing? Your formula for margin of error. You have 3 different formulas for them. Remember, if you don't know the population standard deviation, you have to use a t-score, no longer a z-score. So you're going to need those 2 tables, table B and table C, the z-chart and the t-chart. And it's, of course, more realistic that if you're doing mean, you're going to have to use a t-chart. Because if you already know the population standard deviation, you already know it. So the interval becomes pointless. We only have 2 sections left to cover. Both of them are on hypothesis testing. Hypothesis testing on means and hypothesis testing on proportions. Once again, you have 2 conditions for the mean. Sigma is known, sigma is unknown. The process, again, is going to be identical. It's just, are you using a z-score or a t-score? All right, so the 2 remaining sections are the mean hypothesis testing and the proportion hypothesis testing. That leaves next Thursday as the review day. That means next Thursday is the last meeting. Next Thursday will be our last meeting before the final. This final exam is the 18th, right? Let me get you the time. 3 Thursdays. So it's 3 weeks from Thursday. It'll be in this room, 12:30 to 2:30. So December 18th, 12:30 to 2:30. The date is on the syllabus, just not the time. They do try to keep the start time the same, but finals are in 2-hour blocks with a 15-minute gap. And I think they start at 8. So it's like 8 to 10, and 10:15 to 12:15, 12:30 to 2:30, 2:45 to 4:45, and then anything beyond that is the original class start time.
Wait, so we're supposed to show up here at 12:30?
Yes.
So 2:30?
It's 12:30 to 2:30 is the exam block. I doubt you're going to need the entire 2 hours. I wrote it as still a 75-minute exam. So I doubt you'll need the entire 2 hours for it.
So still, you make it double the time.
Sorry about that. And since it's not comprehensive, I can actually just treat it like a 75-minute exam and just keep it 2 hours. And this one's even easier because it's
Oh, yeah.
it's mostly
It's basically all.
confidence intervals and hypothesis testing.
Just.
And there's also probabilities and random variables in it. I think it's the easiest. I think the descriptive statistics is the hardest stuff, personally. And I did mention the third group assignment is also available now, which will be due on the 11th of December, which is the last meeting.
Are we going to have a unit award test?
Yes, that will go up next week as well. And I haven't, that'll be due on a day that we're not scheduled to meet, that's due on the 15th. And I only did that so I could make these solutions available for the final. So after the due date, I'll make the solutions available. Please go over it before I